Okay, guys, in this video we are going to go over this handout. There is not enough space over here to fit the solution to the problem. These are not actually problems. This is says construct a full model, figure out everything. And because they say figure out everything, we are going to find out what they could ask you in a situation like this. And what is a model? A model is a representation of the reality. It is simplifying of a train moving. So for example, this is one dimension. So this is the x-axis and this is the train. And we are going to pretend that at time 0, the train is right here at 0 seconds. And because they said that start from rest, the train was stopped. That means the initial velocity is 0 meters per second. They are telling you that it's accelerating at 2.5 meters per second squared. This 2 over here is supposed to be here. And it did that for 15 seconds. And now, what could be asked in this problem? Figure out everything. They could ask you how fast is moving 50 seconds later. How fast is moving 15 seconds later. They could ask you what is the position or the final position uh, 15 seconds later. Okay, so we are going to keep it simple like that. Let's find how fast it's moving and where it's located 15 seconds later. This is motion with constant acceleration. We are going to assume that the acceleration is constant. And the implication of that is that you know how the motion is. The motion exhibits a quadratic function for the position and time graph. And the equation is this. And the velocity versus time is a linear function starting from 0. So this 0 over here means from rest. And this is the equation for the velocity. Now for the first case, the velocity, let me write the equation again. You cross this out because it's a rest at the beginning, and you just need to multiply 2.5 meters per second squared times 15 seconds. 1 second cancel, and the velocity 15 seconds later is 37.5 meters per second. That's more than 100 miles per hour. You box the answer because you need to submit this into Focus. Make sure you show all the work like this. So this is how fast it's moving. It's going at 37 meters per second, 15 seconds later. Now let's find the position. Where is it? Where is located 15 seconds later? This is the equation. And the initial position we set up to be 0. Let's pretend that we put the origin where the train was stopped. So we set it up to 0 meters. And the initial velocity is 0, and 0 times 15 seconds is 0. So the position of the object is just 1/2 AT squared, which is this function over here. It's a quadratic function, and if you want to find what it is, just do this math. Remember the time, this is meters per second squared, this is second squared. Because the time is squared over here, this second and seconds cancel, and you are left with only meters. So where is the train located? So 15 seconds later is 280 meters away. Okay, so we have the situation. We just draw it like this: 0 meters, 0 seconds, and 15 seconds later, this distance is 281 meters, and this velocity is 37 meters per second. So this is a model of the reality of a train moving with constant acceleration. We are going to do now the second problem. The second problem is a motorcycle going at 36 meters per second. That's very close to 100 miles per hour. I know at the top of my head that 35 meters per second is around 100 miles per hour. Slam the brakes to avoid an accident. The motorcycle skids 23 meters before stopping. So we have the situation that the motorcycle is here. Let's pretend this is the initial position, 0 meters, and at 0 seconds is right there. And then is here. And this displacement, this final position, is 23 meters from the initial position. So we could consider this to be the final position. At what time that happens, we don't know. How fast it's moving, we don't know. And because they say figure out everything, this is what we are going. And we don't know what the acceleration is in this particular case. In this situation, if you want to do position versus time and velocity versus time graph, the guy is initially moving to the right. Oh, this is the initial velocity. I didn't put it over here. 36 meters per second. So it's over here at 36 meters per second. And slow down to stop. Here is 0 meters per second. Always try to do the velocity versus time graph first, because that's the one that gives you more insight. Position versus time, on the other hand, is at 36 meters per second. So at time 0, the position is 0. The position is 0. And the velocity is 36 meters per second. The slope of this line is not 36 meters per second. Let's pretend it be. I just do it like that. So that's the velocity at time 0. And the final velocity here, let's extend this. The final velocity here is 0. So later in time, let's see, later in time, it's going to be forward. He moved forward 23 meters. So this position over here is 23 meters. but at that time, at that distance, the velocity is 0. So that means the slope of the line is 0. So here is the final velocity, which is 0 meters per second. So I can put that one over here. Final velocity is given. Stop, meters per second, because stop. Then I need to draw a quadratic function with the slope being 36. This is not up to scale. This is slope 1 or 1.5. And a slope 0. So this is what makes sense. See that? The slope is decreasing, decreasing, decreasing all the way to 0. The values of the velocity are decreasing, decreasing, decreasing all the way to 0. So this is the graphical model or representation of this problem. And now let's find some numbers. Let's find, for example, the acceleration, the velocity, how long does it take to be there. So let's put this equation. Always try to use this one first, if possible. And you see the initial position is 0, but the initial velocity is not. And you know that the final velocity, the final position is 23. So this is all given, but useless because time is unknown and the acceleration is unknown. So there is nothing you can do now with this equation because time and acceleration are not given. So this is the first kinematic equation. The second kinematic equation is Bf equals B naught plus AT. And this one we have the same situation. We know the final velocity is 0. The initial velocity is 36. Let's put it over here with the highlighter. This is 0. This is 36. But we don't know what is the acceleration. And we don't know what is the time. Over here we know the final position, 23. We know 36. But we don't know time and t. Time and acceleration. But there is a third kinematic equation that is Bf squared equals B naught squared plus 2a xf minus x naught. As you can see in this one, I know the final velocity, 0. So this is 0. The initial velocity is given is 36. This is 36. And the final position is 23. And the initial position, I set it up to be 0. So in this equation, I can solve for the acceleration. So I got 0, B naught squared plus 2a xf. And I minus B naught squared. Negative B naught squared equals 2a over xf. And now I divide by 2 and final position. And the acceleration is negative, and that's the reason why I stop. It's moving to the left, to the right, but the acceleration is to the left, as you can see over here. And this is the equation to calculate the acceleration. Now I'm going to substitute the numbers to find what is the numerical value of this acceleration. We know now that it's negative because you have that negative and you're squaring the velocity, so everything is positive and you have a negative over here. So you have negative 36 meters per second squared over 2 times 23 meters. You know that the unit of acceleration is meters per second squared, so that's what this is supposed to simplify to. So let's calculate the number. So I calculate the number and I get this. It's very important that you verify that the unit simplifies to meters per second squared, and let's check. the units. So you got meters per second square. So you got meters square per second square divided by meters. Divided by meters. And this is a fraction. So you put meters square over second square multiplied by the reciprocal. And you see the 1 meter cancel. You are left when I pass the alarm. I pass the video, the alarm stops. So this is the second problem. I'm writing big for you to see on the document camera. You are welcome to come to the classroom to pick up this document. So this is the second problem. This is number 2. And this is problem number 2. This is problem number 1. So let's put this together, and this goes into my binder. You're welcome to come and see it anytime. I will also put it like a PDF in Focus. So let's see like a PDF in Google Classroom or in Canvas. Now let's do number 3. A line is thrown upward with a velocity of 5 meters per second. So this is number 3. So let's pretend the ground is over here. And the question is, you throw it from the ground or you throw it from some height? Usually, because your hand is above ground, you throw it from some height. So usually it's like this. And the ball goes up and then down. So you could call that this is the initial position, y. The up and down axis is y. And the across axis is x. So these are called free fall problems, and we prefer to use. So the initial velocity, so y naught is not given, but the initial velocity is given. And there is something that is always given in this problem, that is the acceleration of gravity. Instead of using a, we prefer to use g, and the magnitude is 9.8 meters per second squared. But it's downward. So the acceleration is never going to be asked, because it's understood to be 9.8 if you are in this planet. If you are not in this planet, we will let you know. And what could be asked over here? It could say at what time is at the top position. And this is the problem, what you are going to call final. Let's call this final. But final could be when it's back in your hand, or final could be when it's back on the ground. To simplify it, to make it simple, this video is already 20 minutes long. It's only 2 problems. Let's pretend that we want to find how long does it take to be on the top. On the top, at the very top, for an instant, the velocity is 0 meters per second at the top. And I could ask you, how long does it take to be at the top? How long does it take to go this way? That could be a question. Right. The other thing is how high it is at that time or at that position. And again, if I call my final position where the hand was, I got the same question. How long does it take to be back to his hand? How long does it, etc. But we are going to keep it from here to the top, just for simplicity. These are the kinematics equations. But instead of putting x, you put y. and you put this minus here because the acceleration is negative and the value of g is, the magnitude of the acceleration is 9.8. So this is the way people prefer to put it. However, if you put the axis this way, then this number over here, this plus, this instead of negative is plus. Never do that, you are going to confuse people. And the other equation is the velocity is v naught minus gt. And we know that at the top, the final velocity is 0. So I'm going to rewrite this bottom equation over here, and I'm going to make the final velocity 0. This is given 5 meters per second, and look, we can find how long does it take to go up. So if we solve for t, is minus v naught divided by minus g, or v naught over g. So let's calculate how long does it take to go up. Is 5 meters per second divided by 9.8 meters per second squared. And that's supposed to be seconds. So the time is initial velocity over the acceleration of gravity. Remember, the acceleration of gravity is 9.8 in this planet. An object accelerates downward at this rate, and it takes half a second to go up. Now let's check the units. It's very important to check the units, because if you make a mistake, you catch that mistake by just checking the units. For example, in this case, we have meters per second divided by meters per second squared. Remember that time is seconds, so this is supposed to simplify into seconds. So you have a fraction at the top, that is meters per second, and a fraction at the denominator, so you multiply by the reciprocal, and the reciprocal is second squared over meter. As you see, meters cancel, 1 second cancel, and you are left only with seconds, which makes sense because this is time and times is in seconds. Another question could be how high it goes, or what is the displacement, because I don't know what y naught is. I don't know where his hand was. I could write this equation like this. And put y minus y naught equals v naught delta t minus 1/2 gt squared. And this is the displacement, or the distance from my hand to the highest position. We know what the velocity is 5 meters per second. And now we have the time calculated at 0.51 seconds in the previous part of the problem. So you could do 5 meters per second times 0.51 seconds minus 1/2, 9.8, 0.51 seconds. This is second squared, and this is meters per second squared. You see, seconds and seconds cancel, so you're left with meters, and the displacement upward is in meters. And second squared and second cancel, and you're with meters too. So now I will calculate that. So you see that the displacement is 1.2755 meters. Again, this is, if my final position is the top, this is what I get. But I let you know, there is not too much different if you want to know when he's back to his hand. The time is twice. The displacement is 0 because it's back where it was. The distance traveled is twice 1.27, this path over here. And the velocity, if this is plus 5 meters per second, the velocity is negative 5 meters per second. It's very interesting to prove that out. So, and another set of problem is if you want to find the information at the ground, but to know the information at the ground, you need to know the initial height, the initial position of the ball. So we can stop here. We found how far goes up and how long does it take to go all the way to the top. Again, these are the two equations. How long does it take to go to the top? And how long does it take to be back? Okay, this is number 4. A egg is dropped from a building. So this is the ground, this is the building, and this is the egg. So the initial position is 61 meters and it's dropped, so the initial velocity is 0 meters per second. And let's pretend that the final position is the ground. So the final position is 0 meters because it's the ground. And what is the final velocity? How fast is moving right before hitting the ground? Right before splashing on the ground, how fast was the egg moving? And as I said, the acceleration is gravity, is 9.8 meters per second squared. That is understood to be given. Okay, so you try to use this equation. It's the equation that has more terms because it has initial velocity, initial position, initial velocity, time, and acceleration. But because the final position is 0, is the ground, and the initial position is given is 61 meters, is drop means that the initial velocity is 0, so this term is 0. The equation simplifies to this. And the only thing that is not given in this equation is the time. So we could go ahead and find how long does it take to go to the ground rather than finding how fast it's moving when it hits the ground. So you minus y naught. So minus y naught equals negative 1/2 at squared multiplied by negative, and the negatives cancel out. So you multiply by 2. So get rid of the negative, multiply by 2, divide by a, and take a square root. If you do all those steps, time is twice the height divided by the acceleration, which is g. Supposed to put g. We could go ahead and calculate that. So second square root, control put a fraction, 2 times 61 divided by 9.8. And that gives 3.528 seconds. Okay, so that is the time it takes to go to the ground. Now if we use this equation, is drop, so this is 0, and we substitute that time over here, we know how fast it's moving right before hitting the ground, and we know it's negative because it's moving down, minus gt, so negative 9.8 times 3.528. So you get the number that is there in the calculator and multiply it times 9.8, and that is moving, oh, that's close to 100 miles per hour because 34.57 meters per second. And this is how fast is moving right before hitting the ground.